All right, let's dive right into this explainer. Because look, setting up a Kubernetes cluster, that's a one-time breeze. But maintaining it day to day, well, that is where the real battle begins. We've all been there, right? The deployment is applied, but things go wrong. So today, we're breaking down the absolute most common Kubernetes errors, and more importantly, how you can systematically troubleshoot and fix them. We're going to tackle this structurally across 5 key areas. First, fixing pod and container errors. Second, node and resource roadblocks. Third, networking and access denied. Fourth, cluster control and advanced states. And finally, we'll wrap up with the ultimate troubleshooting playbook. So, Section 1, fixing pod and container errors at the micro level. Let's start right where developers feel the absolute most pain, inside the pods and containers. The dreaded CrashLoopBackOff. You've probably seen this one. When you see your container restarting 10 or 20 times, your immediate first reflex must be to run kubectl logs, followed by the pod name, to find out exactly what's missing. A CrashLoopBackOff simply means your container is failing to start, dying, and Kubernetes is just endlessly trying again. The root cause? Well, often it's a misconfigured readiness or liveness probe, or honestly, even more commonly, you simply forgot to define a required environment variable in your deployment file. The logs will tell you exactly which one is missing. Next up, we have error image never pull. And this brilliantly illustrates what happens when you misconfigure your policies. If you tell Kubernetes never to look outside and the image isn't local, well, your pod is going nowhere. Normally, if an image like Nginx isn't on your system, Kubernetes reaches out to Docker Hub to download it, right? But if your image pull policy is set to never, you have explicitly forbidden the cluster from looking externally. So if it doesn't find the image sitting locally on the node, it just throws the error image never pull error and stops dead in its tracks. Understanding the normal life cycle is absolutely critical here, because it helps us pinpoint exactly where a pod is getting stuck when things go off the rails. A healthy pod starts in waiting or container creating, moves to running, and eventually reaches a terminated state when it either finishes its job or gets deleted. Knowing this baseline is your key for the next troubleshooting step. Because sometimes, when a pod stubbornly refuses to die and is just stuck in the terminating state indefinitely, you can use the nuclear option. Force delete it by setting the grace period flag to 0. You literally just run kubectl delete pod with the pod name and tack on -grace period equals 0, -force. It tells the cluster, hey, stop waiting for a graceful shutdown and immediately remove this resource. All right, moving on to Section 2, node and resource roadblocks at the hardware layer. Let's move out a layer and see how this builds when we look at the underlying hardware. If a node shows up as not ready, this 3-step workflow is exactly how a senior systems engineer isolates the issue and jumpstarts the crucial kubelet component. First, kubectl get nodes confirms that not ready status. Second, you run describe node to read the specific events and errors happening on that hardware. And finally, you restart the kubelet using systemctl restart kubelet. The kubelet is the main agent running on every worker node. It controls exactly how pods are deployed there. If it crashes, the whole node goes offline. So picture this. You apply your YAML, the node is seemingly healthy, but nothing happens. What could possibly be keeping your pods stuck in a pending state? Well, the answer usually boils down to one of two things. Either the node is entirely out of hardware resources, or strict deployment policies are actively blocking the pod from landing there. If your cluster doesn't have the required CPU or memory available to schedule the workload, the pod simply hangs in pending. Alternatively, if your administrators have applied a taint to a node to repel certain pods, and your pod lacks the matching toleration, there is no way it'll ever be allowed to deploy there. Think of this literally like a hardware budget. Requests are what you need to survive, but limits prevent a buggy pod from devouring the whole server and triggering an OM killed or out-of-memory error. The crucial point here is that developers have got to optimize their code. If you don't define limits, a pod with a memory leak could consume 16 gigabytes of RAM instead of the intended 2 gigabytes. That starves every other application on that node. Setting strict requests and limits ensures your pod actually plays nicely with its neighbors. Okay, Section 3, networking and access denied. Now that our hardware is sorted out, we have to look laterally at how these components talk to each other and who is allowed to do what. If a user can't hit your application and you get a service error, it almost always means the backend pod it's pointing to is just not ready to serve data. The service acts as the traffic cop, routing external requests right to your backend deployment. If those pods are crashing or restarting, the service has 0 healthy endpoints to route to, which gives you that frustrating service not accessible error. Now, when you try to access those resources yourself and get blocked, it's absolutely critical to know the difference here. Forbidden means your specific team role doesn't have the permissions, while unauthorized means your cluster doesn't even recognize your kubeconfig file. Imagine a dev team and a test team. RBAC, or role-based access control, ensures the test team can only view the test namespace. If they try to alter dev resources, bam, they get a forbidden error. But if your actual authentication file, your kubeconfig, is missing or completely broken, the cluster will just say unauthorized. Section 4. Cluster control and advanced states at the macro level. Finally, let's zoom all the way out to the overarching brain of the system and look at a few advanced deployment states. Here's a quick pro tip. A container in a completed state isn't always an error. If it's a sidecar container, that just means it's successfully finished its prep work. Usually we run one main application container per pod, but sometimes you need a secondary container, a sidecar, to fetch a configuration or prime a database for 30 seconds before the main app starts. Once that sidecar finishes, it enters the completed state and never runs again, all while your main application container stays running indefinitely. Let's talk about pod disruption budgets. Think of a PDB as a minimum staffing requirement for a retail store, ensuring you never accidentally take your entire app offline during a routine update. In production, your application absolutely must be available 24/7. If you trigger a rolling restart of 6 pods and they all go down at the exact same time, your users hit a brick wall. A pod disruption budget prevents this entirely. So if you set your budget to allow 25% of pods to go down, Kubernetes will mathematically stagger your restarts to ensure users always have a seamless zero downtime experience. The cluster is smart. It'll take down a few pods, wait for the new versions to come online and become fully ready, and only then proceed to restart the next batch. It literally guarantees your application is always serving traffic. But remember this, since your commands always talk to the API server first, if it goes down, your entire control plane is completely blinded until you restart that service. The API server is the gateway. When you run a kube control command, it hits the API server before talking to the etcd database or anything else. If it crashes, you're locked out of managing your cluster. Restarting it is your immediate first step to regaining control. Section 5. The ultimate troubleshooting playbook. Let's wrap up this diagnostic journey by condensing everything we've talked about into a final playbook you can literally use tomorrow. This cheat sheet maps out your immediate tactical response to the most common day 2 operations failures. If it's a CrashLoopBackOff, check the logs. If a pod is pending, jump straight to describing the pod. Node not ready? Describe the node. And if you're seeing forbidden access, you need to go audit your RBAC role bindings. No matter what layer you are troubleshooting, your first instinct should always be to describe the resource, to read its events, and find the root cause. This is the absolute golden rule, folks. Before you go deleting pods or pulling your hair out, kubectl describe gives you the basic idea of exactly what is failing in the background, whether it's a memory issue, a scheduling conflict, or just a bad configuration. Because, let's be real, the cluster will crash again. That's just the reality of software. But now you have the structure to fix it. So what are you going to investigate first? Will you dive right into the pod logs, check the node resources, or audit your network policies? Take these strategies, apply them to your daily grind, and really take control of your cluster. Keep exploring, keep learning, and I'll catch you in the next explainer.